The A-stable multivibrator is another type of cross-coupled transistor switching circuit that has no stable output states as it changes from one state to the other all the time. The A-stable circuit consists of two switching transistors, a cross-coupled feedback network, and two time-delayed capacitors. The basic transistor circuit for an stable multivibrator. The basic transistor circuit for an stable multivibrator produces a square-wave output from a pair of grounded emitter cross-coupled transistors. Both transistors, either NPN or PNP, in the multivibrator are based for linear operation and are operated as common emitter amplifiers with 100% positive feedback. The stable multivibrator are also known as free-runner multivibrator as they don't require any additional inputs or stable multivibrators are also known as free-running multivibrators as they don't require any additional inputs or external assistance to select.
Beginning of the state 1. The shares in C1 is positive, BCC 0.7. The shares in C2 is negative, BCC minus 0.7. When Q2 is found in a cut-off state, it is when the current is not flowing through its terminals. It is practically eliminated because Q1 is in the conducting state. The base emitter junction behaves like a forward biased diode, but at the moment it is saturated. It is when voltage present in transmitter collector is minimal. C2 is charged throughout R4 on the base of Q1, so C2 is charged to VCC minus 0.7 voltage. This charge will be very fast because R1 and R4 will be of very low value compared to R2 and R3. On the other hand, C1, which started with positive VCC 0.7 volts, is now connected in reverse, beginning to download throughout R2. The load will be slower. The voltage VE of Q2 is approximately 0.7, while the voltage at the base is below that value. It will not drive. The base of Q2 is polarized throughout R2. The base of Q2 is polarized through R2.
Remember that at this moment C2 had been fully charged up to VCC 0.7 because when Q2 goes to conduction it connects to earth the positive terminal of C2, while the negative terminal remains attached to the base of Q1. It looks like the capacitor is inverted to Q1. The base of Q1 received VCC 0.7 volts, which take it immediately to the cap. It may even lead to a rupture of the joint by avalanche. Under these conditions, we enter in the state 2. In the state 2, Q1 is in capped, Q2 is in conduction, and the charge in the C1 is negative with a potential. In the state 2, Q1 is in cut, Q2 is in conduction, so the charge in C1 is negative with a potential of VCC minus 0.7 volts, and in the charge in C2 is positive with a potential of VCC 0.7 volts. In the same way that the previous state eliminates Q1 from the circuit, we are going to substitute Q2 for a diode and a bridge. So C1 will range from minus 0.7 volts to the VCC 0.7 volts quickly as R1 is small. C2 is going to slowly unload through R3. It will only get to minus 0.7 volts because when it arrives there Q1 will conduct. It will take the positive C1 to the ground and it will apply to the base of Q2 all the load of inverted C1, taking it to the cap and causing status 2 again. Thus, the cycle repeats itself indefinitely.
For the design of the circuit, it is known that the capacitors are charged by R1 and R4 faster than they are discharged by R2 or R3, because when charging from state 1 to 2, we want the other capacitor already charged, so 1 less than R2 and R4 less than R3. This indicates that R1 equals R4. It takes into account the current flowing through the emitter collector during the charging to avoid burning the transistor, which depends on the supply voltage. R collector resistor. The resistance R1 and R4 should be designed to limit the collector current ESC within the safe limit. R1 equals VCC less VCE less V load divided in IC. R2 and R3 are the base resistors. R2 and R3 should be chosen such that each should give the required collector current during the saturation state. The minimum base current EB minimum equals IC divided in beta is the HFE of the transistors. R2, R3 equals VCC less VB. Safe base current IB equals 10 per IB minimum or 3 for IC divided in beta. R2 and R3 equals VCC less VBE divided in IB. The time it takes to switch from state 1 to state 2 is given by that leads to C1 discharge from the VCC less 0.7 from the VCC less 0.7 volts to 0.7 negative volts. It does this through R2 and using the chair equation to the capacitor we have the next formula where initial voltage V sub 0 equals to VCC less 0.7 volts. Terminal voltage E equals to VCC negative. The final voltage equals to 0.7 negative volts. For the design of the circuit, it is known that the capacitors are charged by R1 and R4 faster than they are discharged by R2 or R3, because when charging from state 1 to 2, we want the other capacitor already charged, so 1 less than R2